It's not loud. We cannot hear you.
Yeah. Okay. Again,
Great.
good morning and welcome to today's class. We are going to be focusing on time series today. I know we've gone through a whole bunch of other topics, and like in other courses, we have a very limited time, to address these topics. So I would say time series all by itself, right? I can literally do time series for an 8 to 12 weeks course. So time series is one of those really very important topics, right? And it's wide. But like every other thing, what I try to do in these classes is to introduce you to the topic, drop a few breadcrumbs, and then go to your the what do you call it, LMS, which is the learning management system that we use. And then that's where I will begin to expand on some of the concepts, some of the things that you actually see in the LSM. We um we some of those things we actually don't even touch them in the class. So it's really, really important that you go through your LMS, watch the videos, or else you're going to be missing some concepts. It's not your fault and certainly not mine, but data science is broad and it requires some real focus if you really want to understand data science. But what I try to do is do what we can do in class, outsource some of the additional knowledge on the LMS system, but I spend time curating the content. There are videos, sometimes articles to read, and then links to other materials that can help you. So I want you to take that outlook as we address time series. Also, I'm going to introduce you to some of the most fundamental concepts. Even in the notebook, I've actually included something there where I've given you like a very simple path to, pursuing additional knowledge in time series. And I would also be uploading a bunch of materials, videos, and all of that for time series. We are almost, somewhere close to the tail end of the class. So what I would say is if you're feeling tired, you need to redouble effort right now and study as much as you can to grasp as much as you can, because the guided opportunity might be something that's gradually fading away with time. So, all right. So I'm going to go ahead and share my screen so that we can just give me a minute. Let me share my screen. Or do I share the entire screen or specific applications? Just 1 minute. Okay, let me share this. Okay, I want to think that you can see my screen now. Please, if you can see
Yes,
my
that's
screen.
correct.
Okay, all right. So, a couple of things that we're going to be addressing rather quickly, right? This morning will be, like I mentioned, a time series, and these are some of the, uh, key objectives for today. And one of them would be, so dear, I can see what you're saying. I think you need to log in and log back. I'm hearing check your microphone or log out and then, yeah, please log back in, log out and log back in. That should address the issue. So you have to recognize and analyze how to recognize and analyze data, um, time series data structures and patterns. That's one of the key things we're going to be focusing on this morning. Apply data, uh, sorry, I keep saying data, time series decomposition techniques, right, to identify the different trends and seasonality. So one of those words you're going to be hearing about today or hearing today will be trends. The other will be seasonality. and I'm going to tell us what trends mean, what seasonality means, and there are actually four of those concepts we're going to be talking about this morning. Then we also see how to build a basic forecasting model using the ARIMA and the exponential smoothing. And then we're going to interpret forecast and evaluate model performance. Kind of, it's along the lines of what we did before, right? When I was talking to us about loss functions. And then we're also going to really not going to um, dig deep into the big data fundamentals and common frameworks like Hadoop and Spark and issues around big data. That's not a major focus of this topic, but because we don't we there isn't enough time, right, to talk about you know big data, which by the way is still very important, and that's part of time series, right? And other aspects of data science, and most certainly AI. I just wanted to mention it, at the tail end of this specific topic, week 6. So, thinking of time series, right? If you collect any sort of data, right? So, for example, if you're someone that works in manufacturing, right, and you're doing a couple of things there and you're collecting data over time, right, that could be a time series problem. Analyzing that data will be a time series problem. So any kind of data that you collect that has a time component, most of them or all of them, I would say, will be some kind of time series problem. Like your CCTVs, of course, you collect data over days, weeks, months, sometimes years, right? But every piece of that data is connected to a specific time. And sometimes some of that data that you collect, right? What happened a second ago might have some kind of effect on what will happen in the next second, or something that happened 2 hours ago could have an effect on what happens an hour after that, or 2 hours after that, or 3 hours after that. All of a sudden, when you see a lot of those time series data, you see that there's a specific pattern, and what has happened yesterday is certainly going to be connected to what happens today. And what happens today can, when you pick up what happened yesterday and what happened today, you can reasonably infer what will happen in the future. Now, that doesn't mean that it automatically happens, because there might be some external changes. There might be some changes in that environment that alter that pattern, but to a very large extent, right? What you would see is that historical data from the past and the present that are related to time can very easily be used to predict what will happen in the near future. So that's that's one of the key ideas of time series. So when I get all of this data, how do I understand it? How do I curate that data? And then how do I analyze that data? There are all kinds of tools in data science to do that. So first of all, we have the classical tools, some of which we are going to talk about today. And then, of course, we also have what I will call your deep learning tools. You know, the deep learning tools become important, right? Because there are certain limitations, right, that some of these classical tools do have. And that's why, you know, um, deep learning tools now become very important, which is why to an extent, you would see me continuously try to push the idea of deep learning to us so that somehow we can get some knowledge in deep learning, because at some point you're going to have to need it, especially if you're going to do data science, data analytics, and everything in between that. So time series. Time series data actually refers to observations collected sequentially over time, which is the point I was trying to make. It is a sequence of data points recorded or observed. And what's interesting about it is that there's some kind of order to it that is synchronous or has something to do with time, right? So mathematically, one of the ways you can actually represent a time series is something like this, right? Y underscore time or t, where your t can be 1, 2, 3, 4, up to some value in the in infinity called t, right? So in this place, right, t is equals to time, and y is the observation at time t. So if I make an observation at t is equals to 1, which is 1 second, right? I record that observation. That recorded observation is your YT, right? So the key difference, between, say, normal data sets and time series data sets, because in the before now, most of what we focused on is we focused on regular, or normal data sets, but this time it's a little different because every observation, right, is tied to some kind of time, right? So that's one of the differences. So for that particular reason, order actually matters, because remember I told you, right? Let's say you have an observation y, equals to no y underscore t minus 1, and then you have another observation at yt, and then you have a third observation at y underscore t plus 1. These are three. You can see that there is some kind of connection between each of them, because they involve time plus or minus some kind of delta t. So that's what we have there. And the other thing, beside that, the order is very important in time series data, is also you have that temporal dependence, which is time. Temporal here actually means time. There is some kind of dependence on the time, because the specific time when that data point is collected, right, is really very important and plays a role in what that data could mean or is and represents. So examples, some of the areas where you can actually see time series data is, for example, your daily stock prices, right? That's an example of time series data. Your monthly sales data, you can reasonably infer that it's time series data. Your hourly temperature readings, let's say you're collecting temperature data, that could be, because in each of these, right, the time component or the temporal dependencies are really, really very important. And web server traffic log, right? If your traffic log, right, you want to know what happened at every second, right? And that log is able to tell you. So every time you go look at an incident that has happened or something, one of the things you're piggybacking to essentially is your time. So, so I'm writing this kind of twice. Now, types of time series problems, right? Some of those types are, for example, forecasting. One of the things you want to do is to predict future values, e.g. your sales next month. So that's a typical problem which could arise from what you have here, your monthly sales data. You want to be able to reasonably infer what could potentially happen next month. Is it 100% guaranteed that what your prediction would occur? Not exactly so. But then it helps, at least it puts you within a certain ballpark. The other one is also classification, identify the categories of a series. That also happens, right? Because in some cases, when you collect series data, one of the things you're trying to look at, especially in manufacturing applications and related applications, is you want to figure out when a fault occurs. And figuring out when that fault occurs, right, might just essentially be looking at the trend of that data, because maybe there is a lower boundary and an upper boundary, but then when that thing exceeds that boundary, it's some kind of anomaly is detected, right? And that way you can separate what is faulty and what's not faulty, which brings us essentially to the next part, which is anomaly detection. Detect unusual events. So you can see it in fraud, equipment failure, which I just discussed right now, mentioned, and you can also see it in cyber security. So in cybersecurity, you can look at data trends in equipment, right? You collect voltage data, you collect current data, and all of that. Usually, those things fall within a band under normal circumstances. But when you begin to see your waves, right, all of a sudden have very high amplitudes. All of a sudden, you're beginning to be like, oh, something has to be wrong here, right? If you get that data and sit down and analyze that data, you can reasonably know when something happened. And with that data, you can actually tell where that problem is coming from, specific equipment, where that problem is coming from. And more importantly, you can actually use it eventually to do predictive maintenance, right? Where you say, oh, this equipment is going to fail at most likely going to fail within the next 2 months or 3 months because you've seen those kind of data patterns, right, in the past for other equipments that failed because they essentially had the same, exact, say, amplitudes and all of that. So that's what time series helps you do. So you can do all of those kind of things. You can also do another problem is filling missing time points because there are times you get all of these data and you have missing data points within that data. You can actually use 2 or 3 data points in front or behind that specific data to be able to predict what the missing data piece will be. So these are all typical examples of time series problems. So let's imagine your time series, what would you call it? Data. For example, let's think of it like a song, right? You're playing music or you're listening to some kind of symphony. Now, when you listen to that music, what you hear is actually a blend of different things, right? You're not just going to hear the voice of the person singing, right? But you're also going to have the melody in that song, right? Which is, you know, so melody in time series speak, just think of it like your trend, you know. That's one of the things you will see in music. And then you can also get a beat, a rhythm, some kind of rhythm. And usually for every song, right, you have a repeating pattern, you might go through one verse of that music and then the pattern changes into the chorus and then it goes back to the same pattern that you had in the first chorus and then it jumps back, right, to you know to some kind of intermission. But one of the things you can find out is that there is some kind of rhythm, right? So that can be one part of that music. And sometimes, like I mentioned, right, there could be the solo, which is the verse, and then there is, a couple of people come in, sing the next line, and then somebody comes in and sings the solo and all of that, right? That happens in music, but those are irregular, but they are still meaningful shifts. They are cyclic. So watch when I talk about trends and seasonality and talk about cyclic, and then you also talk about noise. And how about noise? Sometimes you have some background noise in your music. Sometimes the background noise is part of the music, or some other times it's actually not part of the music. It's just mere distortion that wasn't cut off when you were doing music. So when you put all of these together, all of a sudden you get this sound coming in, right? Except you pay close attention or use some kind of um, time series application to try to extract that data. You think everything that is coming in together there, right, is the same. But someone, for example, that plays bass guitar, you might not even hear it. You're just enjoying the music. But someone that plays bass guitar would hear exactly those big bass guitar lines, right? So that's how time series is. So that's why it says a time series data is exactly like that. What you observe, right, which is your YT, which is this YT, right, is the mix of these different components that have, been put together. So every time series is a combination of what we call trends. The second part of time series data is seasonality. The third part is what you call cyclic, and the fourth part is what you call noise. So it's your TSCN, right? Every single data series, every time series, right, is a combination of those four. So I'm going to take one step back and then let's look at what a trend is. And it's something that's particularly familiar to us. It's just that I'm trying to present it as a holistic package to help explain the idea of time series. So long-term direction, upward or downward, which we already know. So that's what we know even in regular day language. That's what a trend is, right? Those shifts the direction of a line, and that's exactly what it is here, right? So it's like the slope of a hill, it's slowly rising or it's falling over years. We see that's one characteristic of data that you're going to see. There has to be some kind of trend to data. So a typical increase in global temperature over decades, right, is an example of that trend. You can see it in any time series data. So in a graph, it's the smooth curve your eyes follow when ignoring all of the short-term trends. So this is it. So if you go look at something like S&P, um, S&P, um, let's say ticker's symbol, right? Ticker symbol. Okay, let me just say ticker VOO, for example. Yeah. So this is for example, as you begin to look at, let's go to 5 years, for example, or all time. You can see the pattern of that data. This is some kind of time series data, you know. But if you smoothen out a point from this point to this point, it might end up being something like this, right? So the trend, you can always see the trend of that data, especially if there's a lot of data, because sometimes it might look like it's flat, but if you have a lot of data over time, you can actually see whether that data is going up, going down, or remaining flat. So that right there is example of trend. So this is what I use here as an example of trend. These are the values. This is over time, 2020, January, March, up to 2021, June, April, right? So that's the trend of that data. So beyond that, you now have seasonality, which are predictable, repeatable patterns over fixed periods, right? So sometimes, that also occurs, right, in series data, where all of a sudden you see these predictable patterns. These patterns are always there somehow, for different data types, right? They just have some kind of seasonality. They happen on fixed schedules. You can almost set your watch to it, right? It's just like temperature data, right? In the morning it's cold, and then in the afternoon it becomes hot. So if you're taking a measurement of that data, you see those patterns. A lot of things in nature are like that. You see specific patterns of how things behave. You think of the sine curve, your cosine curve, a lot of those there's some kind of pattern to that data. So technically the pattern repeats exactly or nearly exactly every p time steps, number of steps. So this is a typical example of seasonality, if that's a concept that is not familiar with you. And then you also see cyclic, which are irregular waves or fluctuations over long time horizons. So for example, right, there are things that, beside the regular patterns, there are certain times that all of a sudden, some irregular things happen and break those patterns, right? And you will see, for those of you that live in the West, maybe the United States, the UK, where you have a little more stable economies, right? So in some of those places, you can predict some kind of seasonality. But all of a sudden, they are telling you, oh, we haven't had a recession in a while. And you see some of these recessions will happen once every 10 years, or it's something about the housing market, where all of a sudden, sometimes, like right now, the housing prices are just flying and they are really very high. But all of a sudden, something happens and the prices crash, and which is a pickup opportunity for people that have some money at that particular. And for some weird reason in nature, these things happen over and over again. So that's why it says like economic booms and busts, they come and they go, but not on a perfectly fixed schedule, right? It's not like your seasonality that you can almost predict, but these are kind of irregular, but we know they are coming. Housing market cycles, they typically last 5 to 8 years, but not exactly the same length each time. Sometimes it's 5 years, sometimes it's 8 years, sometimes it actually veers outside that boundary. So cycles are often driven by external conditions, things like the economy, market sentiments, and all of that. So this could be an example. Things rise very high, and then there is the trough, and then there is the crest. There's the crest up there, and then there's the trough, and it happens over some time. Somehow, it's irregular but random irregular, but it does happen. And then the last part of it is noise. So if you can expand some of these data piece, right? You expand it very well. All of a sudden, you're going to notice some noise. You notice some noise. You know, if I could figure out a way to open up these places, you see how these things are not smooth, right? Even though what we have here is looking very smooth, but if you expand it, all of a sudden you get some of that noise. And which is this can be an example of expansion, right? And that's where you get these random variations. But when you follow the random variations, right, over a long time, you actually see a trend that is either going up or going down, even though it looks kind of um, this way here. So the static in your song, unpredictable blips that you can't model directly, those are all random kinds of. So sudden temperature spikes from a local event, one-off stock price jumps, and that's where people that trade options, right, make a killing or they lose a lot of money. Some of those, it's some kind of noise that is going on there. So in math, we usually assume this has zero mean. What I mean here is mean of zero or zero mean and some kind of variance. So I wouldn't go back to this because I explained this already. So there are different ways, right, in which you could see these four components, right, being represented in data. In some cases, you have like additive models. So those components, right, which is your T, your trend, your seasonality, your noise, right, your cycle and your noise. This noise can also be referred to as residual. So in some places you see it being referred to as residual. So it's just some addition there, right, to take care of noise. So you have the additive model, right? They are typically good when seasonal or cyclic changes are roughly the same size. So you see those changes, when it occurs, right? It just adds, let's say those changes occur, you expect those changes to occur, right? Everything is within the range, say 0 to 1,000. But every year, right, when that change occurs, there's an additional 500, for example, on top of it, right? Nothing really changes. Whenever that change occurs, there's a fixed amount of additional delta T, that occurs. That's like in your additive model. So an analogy, imagine a flat road with regular speed bumps, right? You're going on this road. Each bump is the same height, whether the road is at sea level or at highway up a mountain. So that road, right, when you're driving down a road and there are a couple of speed bumps, all of them have been designed to be the same thing. They are speed bumps, they are irritating. But even if you lift the road, the entire road, and lift it up, 100 feet up, right, those bumps are still going to be the same height. The only thing that has happened is that your road, right, is higher. Maybe the field under the road is still higher. That's like your additive model. But then there's also the path, right? Your multiplicative model in time series. And what's happening is you're actually multiplying each of those components, right? The components scale each other. Good when seasonal or cyclic changes are proportional to the trend. In some of those cases, you see something like this, a runaway trend occurring. But then one of those things you're going to see, and I think I'm going to I'm going to include a video that you can watch later, right? Where I was watching this guy and he was actually talking about how to work with some of these various components. I'm going to include that in our work, because there are times when you actually have to now take a log of your data as you begin to prepare your data for modeling. So I am going to talk about each of this, starting with stationality, uh, how to detect it and all of that. But just give me a minute. Let me 1 minute. So ab initio, right? I talked about this is what I talked about. Can someone help us with the sound? Just a minute. I'm trying to mute. Sorry, I'm trying to mute. I was trying to mute that sound. Okay, so one of the things I talked about right earlier was the idea of, let me see, the issue of trend, seasonality, cyclic, and noise, right? We did talk about that, which are the components essentially of what you see in any time series data. But let me go back to 3 before we go talk about stationarity. Stationarity that I mentioned in the video. I already put out this slide, but I would change some things around it later. So, you can actually use, this is an example of some data. Notice this data, right? I'm trying to use Python to decompose some kind of time series data. You can actually see the data is some kind of airline passengers data, right? That's what the data is. But what we are doing here is essentially to try to decompose that data, right? Because if you go, when you have time, just copy this because it's a URL. It's in GitHub. You can see the data. But with all of that data, it was you converted, the pandas to date, time, month, and then we came here and then what all of this is doing is actually decomposing the time series, right? Which is that data specifically for this colon, right? And you're using the model, the multiplicative that I talked about earlier. We had the additive and the multiplicative, right? And then that's how you get this result. Guess what it does, right? And then you try to plot it. When you plot it, you get these different data pieces. So this is your original data, which is the passengers. This is what it looked like. And these are airline passengers traveling over time, over a certain amount of time, right? So the number of passengers is beginning to increase over time, but you can also see some of those fluctuations that we talked about that occur. Sometimes they are seasonal, there are all kinds of things. Something might happen and then there is a spike, but essentially you have these patterns happening in nature. Yeah, but you can now decompose that data, which is this data, into different data pieces. You have the trend, and then you have the seasonal, and then this is your residual, right? That's what you have here. So it's possible to get any piece of time series data and actually decompose to see all of the things that we were talking about, I mentioned earlier. So that's one of those. The other thing I wanted to talk about is what I mentioned about the video, right? And this is what you call stationarity. First of all, why do you why is there a need for this? Or first of all, let's actually understand what stationarity is. That's where you want to get your data to. Stationarity means that the statistical character of time series doesn't change over time. Again, I will get to, just let me go up and okay, we talked about this. And then you have strict stationarity and you have weak stationarity. Now, every possible statistical property, at any moment, Doris, I'm not sure why you're drawing these things on. Please stop drawing it. So every possible statistical is constant over time. In practice, we usually care about weak stationarity, or what you call covariance stationarity, right? And that's what we really care about. So, and what are we talking about? We want a constant mean. And what do I mean? What do I mean by the mean? I don't know. So let me go here. Let me see. So if I was to look for the mean of this data, it will go something like, go through this point. If I take the average of this data, it will go through this point. That's what your mean is, right? You have all these data jumping up and down, jumping up and down. If you take the average, right, the average will fall somewhere in the middle of all these crests and troughs, the spikes, right? That would be your mean. But what would be your variance? Your variance is essentially the point from your mean to the farthest point, right? So for example, something like this has a very high variance, because from here to here is a large variance, but say from here to this point is a small variance. So what you want to do, right, is to, one of the things you want is a constant mean, and no upward or downward drifts. And I will tell you why. You also want, so constant mean means you don't want those up and down drifts going on. When you get a mean, you want that mean to be there. And you also want a variance, a constant variance, right? Same amount of wiggle everywhere. That doesn't happen. As you can see from this data, that's not what's happening. But what you want to do is to come to a point where maybe everything, right, falls between 0 and 1 and 0 and -1, right? You don't want this thing going up and down there. And I'll tell you the reason why you don't want that, right? So there's a third thing you want constant autocorrelation structure. The way points relate to their past is the same over time, right? How data from the past relates to the current, to the future. You want some kind of regularity. And the reason why you want that regularity is because a lot of these natural phenomena, you want to be able to reduce them to some kind of predictable model, right? And that's why you want all of that. So what tends to happen is when you get all of that data, you want to be able to um, apply some kind of treatment to that data, right? To bring it within these uh, allowable characteristics that you want. Because remember, you're trying to build a model, or a couple of models have been built, and they were built on the premise that you had a certain kind of mean, certain kind of variance, and all of that. That's the idea, right? So, which is what the gentleman in the video, that I'm going to post will be talking about, right? You get that data and then you manage that data until you are able to get all of these characteristics. And then you can now use those characteristics. You can now, once transform your data to assume these characteristics, you can now plug your data into those models, and then the models will now be useful in analyzing that data. Now, when you do the transformation, right, the characteristics of that data do not disappear. It's just that they are compressed into the form and shape that you want it to be, but the characteristics are still inherently there. So why, this is the point I was making, why does it matter? Why does it matter? Now, classical statistical models like ARIMA, Sarima, and VAR. I'm going to discuss a little bit about these models later, just show you what they are and what they are about. And the important thing is to know that they are classical statistical models. They are mostly statistical models. They are not like your machine learning on AI, right? But they are tools, data analytic tools. They are built on the assumption that the underlying data, or rather data generating process, is stable over time. That's the assumption. But we know that's not exactly what happens in nature. So, for example, many statistical models actually assume that stationarity. And like I mentioned, stationarity is that assumption, that there is some kind of stability to that data. But in reality, that stability is not there, right? So what you want to do as part of your transformation is to transform that data, right? So that it becomes stationary. And then you can now feed that data into the model, which by the way was designed, to accept data that has constant mean, constant variance, and no predictable uh, trend. Now, if your series isn't, notice no predictable trend, right? So you're bringing everything on a line. So those trends are not going to be there, even though originally time series data has trends. Now, if look at what happens if your series isn't stationary, the model will chase the trend or changing variance rather than capturing the real underlying relationships that exist. So that's what happens if your data is not stationary, and that's why you want to transform your data into stationary data. Now, the other thing that would happen, right, if the data is not stationary, it would actually you have forecast accuracy will suddenly suffer because the learned parameters aren't valid for the future. That's one of the things that will happen. So deep learning models like LTSM, that's long short-term memory, and then transformers. Transformers are the models that actually are behind things like your chat GPT and all of that. Transformers is it. And at some point, we're going to talk about transformers because they are really like most of what you see happening around, the performative AI right now are based on transformers. Very interesting concepts. In fact, I saw one of the authors of the paper that led to this. I don't know. I think I don't know whether he was a student in Harvard or but he was somewhere up there in Massachusetts, right? I know he if I find his video, I'm going to include it as part of the class, probably in his 30s or so. He was one of the people that developed that model, which everybody talks about right now, is the basis of most of what you see going on. So one of the major contributors to that discipline. So deep learning models don't require stationarity, but pre-processing to reduce non-stationarity often improves learning speed and stability. So essentially what we are talking about here is, remember I'm talking about that all of these other models, right? They are the classical models. For the way they are designed such that they accept stationary data. And if you don't give them special stationary data, bad things happen. But for deep learning models, which can also do the same thing that statistical models can do, they do not essentially require stationary data, right? You can give them any data and they can, but if you, um, you know, pre-process the data, it actually helps them better. Why? Because pre-processing, you know, would help improve their learning speed and the stability of those deep learning models. So, if you saw the stuff in the video that I referred to, one of the things that the young man talks about there is how to actually convert that data from non-stationary to stationary data, how to fix it, and how to do the transforms. But first of all, how do you detect stationarity? If you just look at the trends in a lot of time series data, you can immediately tell that it's not stationary. But that's not how we do as data scientists. Remember, we are scientists, right? And we are analysts and scientists. So we want to be able to provide some kind of proof. By eyeballing it, you can tell, but the important thing is you don't just eyeball it, you actually test it. And these are two ways that you can test it, right? So you find out that there's a null hypothesis, right? When the series is non-stationary. And you can see in that video how he was able to run the ADF test, which is your augmented decree Fuller test, right? All of those things, like I said, have already been written for you. They are abstracted. You just need to know that they exist, and you have to apply them against the data that you have. And then your, so for example, your p-value, right? If you can create a threshold where your p-value, for example, is 0.05, right? For that kind of situation, you reject the null. And then when you do reject the null, then that data set is likely stationary. And then the other way to do that is to use the KPSS test, which where your null hypothesis actually says that the series is stationary. Now, if your P value is less than some kind of threshold that you increase there, that would be like it's rejecting the null hypothesis. So in that kind of case, it's likely non-stationary. So using both gives you a more complete picture of that data that you're actually looking at. So again, I would include that video, look at that video and see how it's implemented there. And you don't have to rely on just that. You can just go spend some time, Google this, read up on it, look at videos and understand how this is implemented. So when you have non-stationary data, now you've been able to tell that your data is non-stationary and you want to make it stationary. There are two ways which were also implemented in that video. First of all, the first thing is to do the differencing. And differencing essentially means I am taking the data collected at time t and subtracting the data collected at a previous time. Let's say I collected some data yesterday, right? That is t minus 1. And then I collected some data today, which is your yt. Then I will say the data collected today minus the value of the data collected yesterday will give me the difference. And there is a diff method in that video that you all watched or would watch that already shows how to implement the differencing. Now, what does the differencing do? It removes trends. Remember, I showed you what trends are, and sometimes seasonality if done at the seasonal lag. So it can also difference more than once. You can actually difference more than once if it's necessary for you to. So essentially what it does is it removes that trend, right, and flattens the data. So essentially look at, it's almost like something like this, right? This was, let's say, this was data that you collected yesterday, and this is the data that you collected today. It will be something like this minus this minus this minus this. And that's why this minus this will give you 5. This minus this will give you 5. This minus this will give you something. And then that's essentially what is going on here. And that's what differencing is about, right? And then the next thing is you can also do a log transform, right? And what that helps you do is your variance stabilization. I already told us what the mean is and what the variance is. Your variance is that deviation from the mean, right? So if the variance grows with the level, especially for multiplicative effects, right? The log transformation compresses the big values more than the small values. So at the end of the day, what it's doing is actually squashing all of that. The big values will now approximate lower to the small values. But with all of these things happen, the fundamental characteristics of the data is still preserved. All we are trying to do is we are trying to prepare the data so that it can, let's think of a model as having a very small door, like the size of a regular door that you have in a house. But what you're bringing in, right, is so big that it can't get through that door. All we are doing is we are just chopping it up and rearranging it to the size that can fit through that door. That's essentially what's happening with the differencing and the log transformation. So, um, so this is what's happening in a nutshell, but I'm going to focus on this for ARIMA-like models, right? Make it stationary. When we say it, we're talking about the time series data. Make it stationary first. For deep learning, reducing non-stationarity often simplifies the patterns the network needs to learn. That's essentially the most that happens there. Is not required, but it can be very helpful for deep learning models. So for a quick recap, right? So this is an example of a stationary data, right? It's not perfect, but it falls within a range, right? You can see that the mean is flat, right? The variance is steady, kind of, not exactly, but at least it falls within a band, right? To somewhere around here, a little deviation here, but same deviation, but it falls within a band, right? The fluctuations also look similar throughout the time. So this is similar to this, and then you see some kind of similarity. Sometimes it's like a mirror. Again, it's not perfect, but you can see a certain kind of trend. But this is an example of non-stationary series, right? It had the trend is there, and then you have the changing variance. So the variance is smaller around here, but look at the variance. Because if you draw a straight line from here, right, as your mean, all of a sudden, from that mean to this point is large variance, but you notice that around these places, the variance is smaller. So there's the issue of the trend, which is the data trending upwards, and there is also the issue of the changing variance, right? And those two things, you really don't want them. So for this particular non-stationary data, you can see a clear upward trend, and then the variance is also increasing over time. Two things that you don't necessarily want. But then after you do your log transformation, right? If you do your differencing, you're going to get, you can move from here. If you do your differences, you can move from here to here, right? But to get your, to do your log transformation, it can get you closer to what you have here. So this can be that's why we say approximately stationary, but it brings you closer to this, and this is what you can now feed into the model. So here you've notice you've done the log, and you've differenced, right? You've done the differencing. So when you run an ADF test, right, before the p-value is approximately 0.99, it fails to reject that null, the likelihood that it's non-stationary. But after doing it and you run the test again, right? Remember the test we were talking about, you get something where your p-value is approximately 0.0000 something, right? Which might make it fall somewhere around 90 something percent accurate. So this illustrates why we often difference and then do the log transform before applying an ARIMA type model. So one of the things it does is it stabilizes the statistical climate of that data. So I already talked about this. It's the arrangement. I'll have to rearrange that. So so this is an overview of some of what we just talked about. But then look at some of the, let me talk about the forecast model before I do the overview. So, so these are some forecasting models, some of those classical models that I mentioned, right? We'll talk about all of them here. Exponential smoothing, and this is the purpose, right? ARIMA, you have prophets, which came from Facebook and Meta. They look at trend, holiday seasonality, modeling with ease of tuning. LSTM, this is more of a deep learning application, and I think we are going to touch on that somewhere along uh, the class. It's called the long short-term memory, right? It's sequence-based modeling for complex time dynamics. You don't have to turn your data to stationary for it to work with that, even though it's beneficial. So these are some classical models. I know I've mentioned some of them here, right? But this is what your AR means. It's actually auto-regressive. It predicts using past values of itself. So it can literally predict the future using past values. And then there is the moving average, right? Where you do your predictions, the way the algorithm is set up, right? You do your predictions using past forecast errors. And then you have the ARIMA, which is actually a combination of auto-regressive plus differencing that we talked about, and then your moving average, right? And SERIMA is actually ARIMA plus seasonality. We discussed seasonality here. And then you also have your multivariate time series. So most of what you have in particularly machine learning, and deep learning is you have a bunch of these algorithms, you know, for you to understand or do any beneficial work with these algorithms, right? You need to go understand what the algorithm does. An algorithm is just a step-by-step, um, you know, step-by-step instruction of how to solve a problem. So these different algorithms can generally solve a lot of problems, but they do it in different ways. But for you to be able to effectively know which of the models to use at any one time, you need to understand what that model does, how it works, and then you do the application. So one of the things we are going to do is we are going to actually do a specific example of time series modeling using ARIMA, right? So what does the code that I have here? It will prepare your monthly passenger data, right? It will fit an ARIMA model to that data. So some of the things we already discussed here is what's going to happen here. And then it will forecast the next 12 months, what's going to happen in the next 12 months. And then it will plot both the past observation and then the forecast. That's what it does for us here. So, and I did a step-by-step of how, what's going on here. So if you run this, right, this is what you get. So you have from 1949 to sometime in 1961, and then it will now forecast based on all of this data, it will forecast what could likely happen for the next 1 year, which is what we have here, right? So this is a step-by-step, it's the same code, but just a step-by-step application. We already know what pandas is, we know what matplotlib is, and then we go into your ARIMA, which is the model we use to fit and forecast the time series. So we are fitting it and then we are trying to forecast by an additional 1 year. And this is how you call ARIMA. It's from the start model. And if you go to week 0, I put in a video there, an entire video about start models, but this is just one bit, and it's a statistical tool. This is one bit of model there that can be used to fit data, and that's why we're importing it from the start model. So the next thing you want to do is to make sure your time series is properly indexed, right? To add the index. So that's what happens here. So here you convert your index to a data time index. If I have some time, I actually have an entire slide where I focused on how to do conversions in time. Again, like I mentioned, right, when previously, today is 08/09 slash, okay, sorry, most of you are in West Africa, so it's not 08, it will be 09/08/2025. That's confusing to a computer. You need to convert it to some string of numbers that the computer would can ingest, right? So all of these things here, somehow at some point you have to figure out a way to convert them, right? So this particular method explicitly sets the series to have a monthly starting frequency. So in this particular place, this is actually just helping to set the frequency. I want this thing to start on the 1st of January, 1st of February, 1st of March, blah, blah, blah. That's so as frequency and then MS. That's what it does. So it's your month start frequency. We could decide to say, okay, we're going to start on the 2nd of every month. You can do that too. Once you've done that, the next thing it does is that it fits the model, right? So you have your data frame and then you choose your passengers and then in what order you want to do it, right? Now, if you go look at this model and look at the syntax, it will explain what each of these is doing, but this is what I've brought out here, right? So in this case, the first one is your P, which is your 2, and then D is 1, and then your Q is 2. I've explained them here, which is P, which is equals to is the number of autoregressive terms, okay? And that means past observations used for the prediction. D1 is differencing order, the order in which the differencing occurs. You remove trends to make data stationary. And then the number of moving average terms, right? Past forecast errors used. So essentially, that's what's happening here. And then this particular, you see what we have here. And we haven't talked about optimizers. We're going to talk about optimizers when we talk about as we proceed into the deep learning. But then mix heater, it lets the optimizer run longer if it struggles to converge. It's almost like increasing your what do you call it? The number of steps or time that the system is supposed to cycles, like your epoch that the system is. So you can actually use this to set that. And then this dot fit method estimates the parameters of the ARIMA model using the maximum likelihood estimation. And then again, you can see all of this because I've carefully laid everything out, and that's how we get to this point. So the first line, right, which is your blue line, they are the observed line that we've gathered data on, and then the red line here, please ignore this red here. The red line here, right, is the prediction. So this code is about the same thing, but the difference here is that we included like a confidence intervals, right? So that we can get some kind of data around how much confidence you have in the data. And then here is where I just mentioned a couple of things about big data analytics. You can just read that up. And before I actually go there, let me talk about this. So this is supposed to be just, excuse me. This is supposed to be 7. And then I'm gonna go down, and this is supposed to be 6. Sorry about that. This is supposed to be 6. So all of this is big data analytics, talking about volume, velocity, that those are the things that the 4 V's that make that make something big data, makes data big data, and then the big data ecosystem, right? These are all tools that you can use to manage all of that data, because time series data sometimes can be a lot of data that's been accumulated over sometimes decades, and you want to analyze that data. You need big data tools to be able to manage that data so that you can curate and get the information you need. And then this is essentially a comparison between traditional analytics and big data analytics, right? For traditional analytics, we are talking gigabytes, but for big data, we're talking of terabytes and petabytes of data. Here in traditional analytics, which is kind of what we are doing now, you can use R, you can use Python, you can use Excel, but these things, it will be too much data for them to manage once you bear into the domain of big data analytics. And that's where Hadoop, Spark, and NoSQL become very important. And how about storage? You can literally store some of your data in your local disk, relational databases, and all of that we talked about earlier. But for this, you actually need distributed file systems, right? Because you also want to store them in such a way that the computers can have access to them. And these, in traditional analytics, we do batch. But here, which is a lot of times what happens with production systems, you're doing batch and you're also doing real time. So I'll go back and finish 6 that I was talking about. Remember, I had talked about classical models, but then the only way to deal with time series data is not just classical models. You can also now use deep learning models, as we have gathered more knowledge around deep learning, which is why the from I think it's next week, we are going to start the whole NVIDIA certificates that I talked about the last time, because it's going to kind of introduce us to some of these too. So, and I'm going to have to put up specific assigned videos and materials that you can, find time to read up on some of the deep learning materials, I have a particular video that is um, it's a couple of 10 minutes videos, but I think it will give you a quick intro, which is the specific video I shared in the beginning of the class. I'm going to share it again, and I'm also going to put it in your classroom slides. So, but why do we use deep learning instead of classical models in some instances, right? Part of the problem is that classical models struggle with nonlinear patterns, multiple inputs. If you have multiple inputs coming in, and they're all dependent on that time series, sometimes kind of slows things down. And then if there are long-term dependencies, sometimes the summary is sometimes when the data is complex, classical models struggle. And that's where you now bring in deep learning models. Now, these are some architectures. I hope we can find time somewhere to talk about these different architectures, or at least, at the very least, I will try to assign you some reading that you can read by yourself, because I think they are actually a whole lot easier if you read to understand them. The key architectures are like your RNNs, recurrent neural networks. You have your LSTM, which is your, you know, long short-term memory, and they arose because, so a lot of the architectures that you're going to run into, a lot of them came into being because a previous architecture, right, solved a problem, but there is a part of that problem that it did not solve. So people will go ahead and create a variant of that model. So a lot of times it's not the practitioners like yourself and I that build those models. It's people that essentially get federal grants, sit in their labs and develop those models, right? That end up creating those models, and then they become popular and everyone now begins to use them. So I say that to mean you don't have to try to break your head, right? To create a model of your own, not necessary. The models exist there. What you have to do is study those models, understand what they are, and then their applications, and then use them as at when necessary. That's your own task, and that's your own responsibility. That's what you're supposed to do. And if you do that, more than likely you'll be fine. More than likely you'll be fine. So you have the CNNs, but here for time series, you specifically use temporal CNNs. CNNs are used for pictures, they are used for all kinds of things, natural language processing, and then transformers, which is the ones I was telling you, right? That are behind a lot of the chat GPTs of this world and their various variants. That's transformers. These are different architectures. So when you have time, look them up, watch short videos on them. There are tons of information about them. Key processing for deep learning time series, right? Normally you do a normalization. We're not doing a lot of this deep learning, so I'm not going to go very deep into this, but I just want you to know that they exist. Normalization, windowing, and then feature engineering, lags, rolling starts, and all of that. NVIDIA actually has a whole thing on a whole certificate on time series. So, and then performance metrics, we did talk about this the last time we were, and I put out a lot of materials for you to study, which is your mean absolute error, you know, your mean squared error, MEPE, your accuracy, F1 score, if you remember precision, recall, and all of those things. And then your ROC, AC, and then there's the forecast evaluation, out of sample testing. Those are all some of the ways that you can measure the performance of your time series model. And then if you really want to learn some more about this, these are kind of things you need to focus on. The foundation will be understanding like the components that I talked about today. Stationarity is another thing, indexing, resampling, you learn about that. And there's a lot of free content online. You actually familiarize yourself with ARIMA, SERIMA, and VAR. And then for the deep learning models, you have your RNN, your recurrent neural network, LSTM, GRU, and transformer for time series. And then some more advanced topic in this area will be multivariate forecasting, probabilistic uh, forecasting, and hybrid models. So as you can see, this is a whole discipline of its own self, right? But the important thing is that you know about these things, and if there's any reason for any reason you have to work on a project around time series data, or at least um, you need to talk about it, at least you have an idea of what you're talking about. And these are some suggested readings, that you can also take advantage of. I would have to check on. But in the classroom, we are going to have a lot of that to share. So I think I'm going to stop here and let's catch a break of maybe 15 minutes, and then we'll come back, and then the next 45 minutes we'll go through a couple of things, and I make sure everybody is good, find out where you are, and make a couple of announcements, because you all have to start getting ready to do your presentations. And we'll have to figure out how we'll go about doing that. All right. Thank you so much. And I will talk to us in 15 minutes. So we're about to get into the next hour. So for those of you in Eastern time, it's going to be 11:15 that we get back. And for you in West African time, that would be whatever the next hour is, 15 minutes after that. That's when we're going to get back. So see you all in a few. Thank you.